Electronic configuration of elements. According to the Bohr's model, an atom consists of a central part called the nucleus, which contains positively charged protons and electrically neutral neutrons. The number of protons in an atom is called its atomic number and is represented by Z, while the sum of its protons and neutrons is called its mass number, which is represented by A. Besides protons and neutrons, there are negatively charged particles called electrons, which revolve around the nucleus in various shells or orbits. This arrangement of electrons around the nucleus of an atom in various orbits is called its electronic configuration. Please note here that the number of electrons in an atom is always equal to the number of protons, which makes the atom electrically neutral. Every orbit has a certain capacity to accommodate electrons. According to the Bohr-Bury rules, the maximum number of electrons that can be accommodated in a particular orbit is determined by the formula 2n squared, where n denotes the orbit number. For the first orbit, n is equal to 1. Therefore, 2n squared is equal to 2. Hence, the maximum number of electrons that can be accommodated in the first orbit is 2. Similarly, for the second orbit, n is equal to 2. 2n squared equals 8. Hence, the maximum number of electrons that can be accommodated in the second orbit is 8. Although the third orbit can be occupied by a maximum of 18 electrons, when 8 electrons are occupied in the third orbit, a certain degree of stability is given to the atom. Hence, the next electron, instead of entering the third orbit, goes into the fourth orbit. For example, the atomic number of potassium is 19. Therefore, there are 19 electrons revolving around the potassium nucleus in the potassium atom. Out of these, 2 electrons enter the first orbit, 8 in the second orbit, the other 8 enter the third orbit, and the remaining 1 electron, instead of entering the third orbit, enters the fourth orbit. Hence, the electronic configuration of potassium is 2, 8, 8, 1. The electronic configuration of an element also helps us to decide the position of an element in the periodic table. The number of orbits or shells denote the period to which that element belongs. Let's continue with the same example of potassium. Its electronic configuration is 2, 8, 8, 1. This means there are 4 shells in an atom of potassium, and therefore it belongs to the 4th period of the modern periodic table. Similarly, sodium with 3 shells belongs to the 3rd period. Lithium with 2 shells belongs to the 2nd period. Rubidium with 5 shells is placed in the 5th period, and so on. The number of electrons present in the outermost or valence shell of an atom decides the group number of that element. Thus, potassium with 1 valence electron fits into group 1 of the modern periodic table. Magnesium with 2 valence electrons is placed in group 2. Aluminium with 3 valence electrons belongs to group 13, and so on. However, there are a few irregularities shown by some elements in their configurations, such as that for chromium, copper, silver, gold, etc., which we will study in a separate topic. Despite these irregularities seen among the elements, it is possible to predict the position of most of the elements in the periodic table from their configurations, and vice versa. Summary: we have seen that the number of protons present in the nucleus of an atom denotes its atomic number. while the sum of its protons and neutrons denotes its mass number. The atom is electrically neutral as it has the same number of electrons as protons. The number of orbits in an atom of an element tells us the period to which that element belongs, while the number of valence electrons decides the group number of that element in the modern periodic table.